Hello. Good morning. Thanks for showing up for the session at 9 a.m. Good. So today this is the second day of the workshop. If you just woke up, this is the multiple phases of quantum proof, and today we're going to have a set of very, very great speakers, and they are going to talk about mostly the interplay between quantum and cryptography, and the general theme of the day is sort of upgrading the cryptographic foundation to the presence of quantum computers, and see how the interplay with quantum information theory and cryptography pans out in the process of doing so. Right. So today we have, as I already mentioned, a list of great speakers, and the first is Zvika Brakerski. I'm sure he needs no introduction, but he told me not to make a big deal out of it, but I think it's a big deal that he's here. It's a great pleasure for me to introduce him. I mean, you probably all know the work of Zvika. He pioneered the area of lattice-based cryptography, and his work was recently recognized with the Gödel Prize for the first fully homomorphic encryption from LWE. And today he's going to talk about lifting classical cryptography. Please, Zvika.
Hey, thanks. Woo! Hey. Hey, everyone. Actually, can I have the portable microphone also in case I want to sort of wander around? Yeah. Yeah. Okay, sure. I'm here for now. Hi, everyone. So this is not the title that was advertised, I guess, in the workshop homepage, but we'll get there also. As I mentioned in the session yesterday, while I was sort of preparing this talk and preparing the talk for yesterday, I wanted to give like a little bit of context on sort of what we're doing, what is sort of the grand goal that we have here in the field, and sort of this will give a little bit more context on sort of why we're trying to do a lot of things like what I was talking about yesterday and what I'm going to talk about today. So it's going to be brief, and then I'm going to talk about the specific result a little bit. So the goal is to sort of try to figure out what we're doing with what we're doing. Oh, also I should say that this is kind of, we're in an intimate forum, so feel free to ask questions or tell me to talk about other things. I'm happy to do whatever the audience wants. So the question that I was going to talk about is what to do with classical cryptography now that we're thinking that quantum computers are coming up. Right, so for decades, people have been working on classical cryptography. They didn't have this quantum thing in mind, and they had some great ideas and great insights and great results and great proofs and great theorems and great definitions. And we don't want to give all that up now that we have quantum. Now that we are hoping to have quantum computers in the near future. And the question is, do we have to restart research in cryptography now that we're considering the quantum setting? And I wanted to sort of give a cartoon timeline of how people thought about this question. I actually don't know, like most of this timeline, sort of I wasn't around in the research community, so I could just guess what happened. But this is sort of how I'm imagining things happening. So sort of around the 80s, people sort of figured out that you can sort of get new cryptographic capabilities from quantum, like quantum money or quantum key distributions. And these are things that we sort of couldn't do at all with sort of traditional classical cryptography. But then you're saying, well, I'm going to use quantum for these quantum things. But old crypto, it's possibly fine. We don't need to do much about it, maybe. Because these quantum computers, well, they can do like very limited things. They're not going to. They don't seem to have like algorithmic capabilities that are extreme. And of course that all changed with Shor's algorithm, and then I would imagine people thought, oh, all is lost, right? Factoring is polynomial time, discrete log is polynomial time. Maybe this is an indication that all cryptography can be broken with a quantum computer. So it's possible that we're all doomed, and you can actually see this sometimes in like popular media where people say, well, because quantum computers break a lot of classical cryptography, we have to use quantum cryptography, like quantum key distribution, in order to provide security in a quantum era. But sort of soon after, still in the late 90s, I think people realized that it's probably not the case, that computational cryptography still sort of
should survive. We have things like lattice assumptions, and we can probably just, maybe the hope is that you can just sort of take everything that we did that people did, not we, people did from factoring a discrete log and just convert it to be like based on lattices or things like this, and then we're going to be fine. But mostly I think sort of the thought was that we need to sort of replace the assumption. So we had an encryption scheme that was based on factoring. Now we have encryption schemes that's based on lattices. That's it, we're done. And I think as time passed, people sort of realized that some stuff still goes wrong, even if you base things on lattices. So for example, if you have interactive protocols like zero-knowledge proofs, it's not enough that you replace sort of the basic building blocks, I don't know, commitments or whatever you're using, the things that are sort of based on lattices. When you try to actually do the proof and you're considering a quantum adversary, it still seems that some of the techniques that were used cannot be used anymore. And sort of we need to think, like, so it's not clear that just replacing the assumptions is going to solve all of our problems. And this sort of evolved over the years, I guess, and we figured out things that can be done against a quantum adversary, and some things that cannot be done. And we're sort of trying to understand which is which, and I think this is sort of where we're standing here. And sort of what I'm trying to advocate is that, you know, at this time we should maybe try to think about sort of doing a more systematic study of these things. Maybe we have sort of a bunch of examples, and this is actually sort of starting. You can see this in literature now, and sort of the grand question is how do we use classical cryptography in the quantum age? And one thing is to sort of do it systematically, to sort of know what we're doing, so sort of not just try to do ad hoc, but sort of understand where things stand in the bigger picture of things. And the other task is to try to do things as generically as possible, so try to convert like a whole class of techniques or constructions or things like that from the classical regime to the quantumly secure regime. And I think this is sort of where we are right now. And I'm, you know, maybe you're thinking that this is all trivial and you already know that this is what we're doing, but I figured it's still sort of worth pointing out that this is sort of the effort that's been going on. I mean, it's not a suggestion. This is actually happening now in the literature. So, and the result that I'm hopefully going to talk about today is also going to sort of try to fit in this box, and sort of trying to sort of think systematically about sort of a class of cryptographic reductions in the classical world, and think what they mean in the quantum setting, and sort of try to formalize it. So before getting to the actual result, I want to sort of say a little bit more about sort of these efforts to lift classical cryptography. And again, so these are things that people who are sort of, I guess, going to talks in the area have probably seen, but I think maybe it is useful to sort of give it a name so that we can sort of refer to it, not in this talk, but sort of in general in research. So we're thinking about, say, the construction of a classical primitive, P. Let's say, think about an encryption scheme, and we're showing security against some class of adversaries, let's say probabilistic polynomial time. This is usually what we do. And now, sort of, how do we, you know, what are the possibilities of lifting this to the quantum regime? So the first thing that you can ask for is to have post-quantum security. So you're going to have the same classical construction, but you want it to be secure against quantum adversaries. And of course, the best that you can hope for is that maybe you can just use the same construction, the same classical construction that's maybe already implemented and so forth, and just show that even quantum adversaries cannot violate the security of this construction. So this is sort of one class of lifting that you can hope for. Just take the classical construction and maybe try to modify the proof. And again, the question is where you can and cannot do this. The other thing that you can ask for is maybe you can sort of use quantum capabilities in order to improve some properties of your, still I'm thinking about a classical primitive, so still I'm thinking about something that encrypts a classical message, but let's say if I use quantum communication, then I can do better. So you can think about quantum key distribution also in this context a little bit. You can think about, so for quantum commitments, for example, we have better constructions with quantum communication than with classical communication. And again, the question, an additional question, other than sort of just constructing these things, is how they fit inside cryptographic primitives. So once you sort of use, let's say, quantum communication, then you're necessarily going to change alter your security definition and your functionality a little bit. And we still want to sort of, if we're using encryption or commitments in a bunch of protocols, we want to have these sort of quantum definitions to be compatible with the way that we use things in protocols, so that we can just say, oh, okay, we had a protocol that used, let's say, classical commitments. We should be able to replace them with quantum commitments for classical messages and still have a secure protocol, or at least have minimal changes to the proof for things to work. So this is sort of an effort in this dimension. The last class of lifting efforts that I wanted to mention is sort of trying to find quantum analogs of classical primitives, and sort of, if you've seen my talk yesterday about the quantum garbled circuits, this is sort of one example, or the talk yesterday about actually, no, the talk about the deniable encryption actually fits into maybe into the quantum enhanced, because it was deniable encryption for classical messages. But say quantum garbled circuits fit into this sort of quantum analog, and there's a lot more examples. I shouldn't have mentioned my talk yesterday, but I did. So we are inspired by saying, well, in order to construct some interesting cryptographic primitive, we're taking this, and this building block, and now we want to do a quantum bigger primitive, and we're going to utilize quantum versions of the building blocks and put them together. So this is sort of another sort of effort that we have in the community, and we're seeing a lot of results in this form. So this is sort of what I wanted to say as like a general introduction, and what I'm going to spend, I guess, most of my time on is a specific result, a specific attempt to try to convert classical constructions into being meaningful in the post-quantum setting, and essentially sort of more trying to think what it means to be meaningful in the post-quantum setting along the way. Good. So this is the result that I'm going to introduce, and this is joint work with Nir Bitansky and Yael Kalai, and the question here is about reductions. So can we take classical reduction? So reduction is like, I'm going to say it in more details in the next slide, but can we take a reduction between two cryptographic problems and convert them into the post-quantum regime? And reductions are an essential part of cryptographic literature, and actually also in complexity. And we have a lot of reductions. There's a lot of reductions in the literature, and it would be a waste to just sort of waste them. And the question is, to what extent we can actually sort of reuse these proofs also in the post-quantum regime, in a regime where we're dealing also with quantum adversaries. So yeah, let's go in a little bit more details as to what I mean when I'm talking about reductions. So reductions have been with us for a long time in computer science, I guess since the founding days of Turing. And the point of a reduction is an algorithm, and the purpose of this algorithm is to show that solving some problem P is no easier than solving some other problem S. And just for like examples to keep in our mind, we can think about the problem P as the security of Regev's encryption scheme, for example, and the problem S as the hardness of the learning with errors problem. And I didn't say what any of these are, but you don't really have to know. It's just two sort of cryptographic problems, such that we want to show a relation between them. We want to show that breaking the security of an encryption scheme is no easier than solving some computational problem that we believe is intractable. And I'm going to rest my hand for a second. But you can still hear me, right? Good. And the way that we're going to do this is by showing an algorithm that is given black box access to a solver for P. So we're giving someone saying, well, if I can solve the problem P, violate the security of the encryption scheme, of Regev's encryption scheme, then I should also be able to solve the problem S. I should solve the learning with errors problem. And usually, and actually in the context of this talk, we're only going to consider black box reductions. So an algorithm, it has black box access to a solver, to some algorithm, potentially an algorithm that violates the security of the encryption, and you want to solve the learning with errors problem. And well, the question that we're considering is whether you can take all classical reductions and translate them into the post-quantum regime. So what does it mean to translate into the post-quantum regime? Well, now we're saying, well, assume that you have a quantum algorithm that solves the problem P. We want to be able to
using black box access to this algorithm, obtain, again, a quantum algorithm that solves the problem S. So we want to be able to do this because, well, we know a lot of these reductions, and we want to know them also in the post-quantum context. And people have been thinking about this, and it turns out that this is not always possible. In particular, there seems to be a problem when the problem P is an interactive problem. So in the case of encryption scheme, it's not necessarily interactive because you can just say, well, I'm just sending you like a public key and a ciphertext, and you need to tell me what's encrypted, whether it's encryption of 0 or encryption of 1. But you can also think about interactive security games. For example, even in the context of encryption, we sometimes have this notion of CCA secure encryption, where the first you get a public key, and then you can ask some queries. I can ask you to decrypt some messages for me, and only then I'm going to be able to sort of break the security of the encryption. So you can think about these interactive security games. They're very common. You can also think about protocols, zero knowledge, and so forth. In this case, it seems like when you try to go into the quantum regime, you at least need to think a little bit. Because a lot of these reductions, actually not for the example of CCA security, but for zero knowledge proofs, for example, they use a technique known as rewinding. And essentially what happens is that you're going to take the solver, the P solver, the solver for this problem P, and it's an interactive process. You're going to start playing this security game with P, and then you're going to say, okay, so P solver, what would happen if the next message that I send you is message X? And then you sort of go down the line with the interaction, and then you sort of go back to the same point and say, actually, you know what would have happened if I sent you message Y instead of message X, and try to sort of follow down that path. And from looking at these multiple paths, you're going to be able to get some information that would allow you to solve the problem S. And you can do this you don't even need to think about it much in the classical setting, because if you have access to this P solver, then obviously you can just sort of remember the state that it's been at some point in time and then just go back to it. So this is rewinding. And in the quantum setting, we sort of have a problem. This is what I'm saying is really sort of not new. A lot of people thought about it, and this has been like at least for 2 decades that this problem is known. In the quantum setting, since each of these sort of steps in the interaction could involve a measurement of the internal state of the prover, we run into a problem which is sort of illustrated by this handsome gentleman, which you may think is this Hollywood celebrity and coffee capsule presenter George Clooney. But actually, if you notice the Dirac notation, you'd realize that this is in fact George Clooney. And George Clooney is, believe it or not, the official spokesman of the quantum no-cloning theorem. And we know that in general for quantum states, we cannot duplicate a quantum state. Are you even allowed to mention coffee capsules in Italy? Is that illegal here or something? Okay, anyways, George Clooney says no, you cannot clone a general quantum state. So in particular, once we performed a measurement and went down path X, we cannot in general go back and try path Y. So there's a problem with interactive, problems. But okay, so let's put that aside and think what happens in the non-interactive case. So we have a black box reduction. And it's in a non-interactive setting, so the problem P is non-interactive. It just gets its challenge and sends a response. And you think liberal media would have you think that this is safe. You have no problem at all. In this case, you shouldn't have a problem because, well, with black box access, you can't even distinguish between a classical and a quantum algorithm. It just takes a query and sends back an answer, and we don't care about the inner workings of the solver. And sort of what we sort of try to advertise in this work is that we need to think about it a little bit more carefully, in particular in the setting where we have quantum auxiliary input, which I'm going to talk about in the next slide. And the claim is that there is this setting with quantum auxiliary input, and the setting is both important and is non-trivial to handle even in the non-interactive setting. So this is sort of in the context of thinking not only about sort of translating the result, but also about the meaning of the result. What do we want from a meaningful lifting from the classical to the post-quantum regime? So let's talk about these black box reductions and quantum auxiliary input. So let's consider sort of the timeline of the execution of the reduction.
go back to walking around. I'll try to hold it here so that it's not too loud. So let's think about the timeline of executing the reduction. So we have an input for the problem S. So this is X sub S here on the slide. And we want to make use of the P solver in order to obtain an answer, Y sub S, the response to this challenge. And what we do, the reduction sort of does, like takes X sub S, does some computation, so on and so forth, decides on an input that it wants to send to the solver for the problem P. It sends the XP sub 1, gets the response back, thinks about it a little bit more, sends the next query, and so on and so forth. Maybe it makes n queries overall, and then in the end, it sort of looks at everything that it has seen so far and decides on the answer for S. So this is sort of in general what happens. But in many cases, we're also considering non-uniform adversaries. So non-uniform adversaries are adversaries that are also using an advice string. So this is a string that came from somewhere and is required for this attacker to work. So the attacker, the solver, I call it a solver, I shouldn't change my terminology. The solver for P is required to have this polynomially long string. It doesn't know how to compute it, but once it has it, it can solve the problem P. And well, you know, if you're just thinking about a uniform classical reduction, then it should also work even if you have this auxiliary input. So this auxiliary input is going to be like something that I'm going to sort of assume for the remainder of the talk. So let's take a minute to think. You know, this is like something that is the standard sort of design paradigm in cryptography, or also maybe in complexity theory in many cases. But let's still take a minute to think. Maybe we don't even need to consider auxiliary input at all. So where does auxiliary input come from? Well, you can think about maybe it's possible that you can work hard like once, do an exhaustive search or something like this, and then sort of come up with one long string, polynomially long string that would help you to solve P once and for all. And this would be sort of pretty good. This is maybe sometimes the motivation in cryptography. You're saying, well, I have, I don't know, 2 to the 128 bits of security, but it doesn't mean that if I work once 2 to the 128 times, 2 to the 128 time, then I should be able to solve the problem once and for all. I should still, like for every challenge, I should work hard. So this is sort of one place where you could sort of get auxiliary input. Another case, which is, I think, also fairly common and fairly good motivation, is when you have an intermediate state in execution of a protocol. So you could think that instead of like one problem P, you actually have some distribution over problems and distribution over solvers. And actually, usually what happens, you're going to execute a protocol, and then in some sort of midpoint of the protocol, internal, so you can have sort of a problem P, which is relative to the transcript of the protocol so far, and then sort of the internal state of this adversary that you have becomes an auxiliary input. So this is also something that could happen. Or you can say, well, I just don't care. Maybe it's a tip from friendly aliens. We stumbled upon it by accident. So this is, or maybe even you can think about, if you believe that everything in the universe has to be polynomial timed, then you're saying, well, if this string came about, then some process has to have generated it. But maybe it's just a polynomial time process that's very long. Maybe it's like n to the 100, and you don't want to run n to the 100 all the time, and you just want to sort of be able to use this short string once and for all. So these are some reasons why you'd want to use auxiliary input. Another reason is just that it's more convenient. It sort of gives you a more general framework, and it's sort of easier to compose it down the line. So this is, yeah, questions? Need to wait? Want to take this one?
Yeah, no, works, thanks. So, just a clarification. You mentioned you're considering non-interactive reduction. In which sense is the reduction that you described above non-interactive, or shall we think about that as interactive?
Non-interactive primitives. So P and S are non-interactive.
I see.
Yeah. The reduction you can think about, actually, I mean, you can think about it as reduction. You can think about it as an interactive process between the reduction and this P solver. But I'm talking about non-interactive primitives. So the primitive P just takes an input and spits out an output. This is what I mean by non-interactive.
Thanks.
So yeah, now that we stopped, any other sort of questions or like objections? So this is objectionable, but I mean, okay. Please object. So I guess so this, what is the sort of class of reductions that you're thinking about here, right? Because like an interactive reduction. You said asymptotic. Sorry, no. The class of reductions, like an interactive reduction, you can also like write in this shape, right? Well, okay, so before I noticed before that like people who are standing on the podium cannot understand the questions, and now I get it. Yeah. Like I'm not sure if it's the mask, but let's try. Maybe is this better? Okay, let's try. So you can like you know at least classically you can like write down a reduction with an interactive adversary as like something like this, right? Where these x's are now like they're sort of correlated with each other. Right. Yeah. And this like so you're not considering like this class of things as like a restricted. So in what I mentioned so far, the x's can be arbitrarily related to each other. So I'm thinking the reduction is completely adaptive and can do whatever it wants. So later down the line, when we talk about the results, I'm going to sort of limit myself to a specific class of reductions. But right now, I'm just talking about the problem, not the solution. I see. So then I guess in this picture, you can actually put in non-directive. You can put in reductions with interactive. Like classical reductions with interactive machines do actually look like this. The reduction is an interactive process. So only P and S, I'm assuming, are non-interactive. The reduction itself, you can think about it as an interactive process, except like it's interacting with an adversary that is just it doesn't have an internal state, which I guess I'm getting ahead of myself. Right. But since you asked, since you give me this sort of plug for the next slide. Right. So we can actually think about it almost as an interactive process, right? So we have the reduction and we have this P solver, and they're exchanging messages between one another. But the important point, and the reason why a lot of these reductions work, is that sort of between each sort of query that I make to the prover, I'm actually resetting it to its initial state. So the prover at this point sort of implements the prover. I'm saying sorry. The P solver in this point actually implements the same functionality as the P solver at this point. And this is actually important for reductions to work. And well, soon we'll see that we may no longer assume it in some interesting setting, and then we'll see what we need to do. Okay, so I just want to say that something that is, again, sort of almost ignored in the classical setting because it's trivial, is that once you have this auxiliary input, well, you can run the reduction the same way as you did before, and also, you know, after you're done and you got your output y sub s, you still have the auxiliary input, and you can use it again if you want to sort of solve p again or solve s again. Then you can sort of keep using this auxiliary input. So you're using it many times for your reduction, and then you can keep going. I mean, it doesn't go anywhere. Okay, so I'm probably just going to be able to talk about the problem. It's okay. Okay. What else I want to say? Oh, yeah. So, yeah. What do we want? What do we want from reductions with auxiliary input, or what we want from reductions, I guess, in general in cryptography? So, a useful property that you want to have for cryptographic reductions is this sort of win-win paradigm. So, what is the win-win paradigm? Well, we're saying. So let's think again about sort of S being the security of an encryption scheme and P being some computational problem. So we have one of two options. So either our encryption scheme is secure, in which case we're good, but the reduction tells us that if the encryption scheme is insecure, then we're also winning. We also have a win, but we have an algorithmic win. We get a new algorithm for a problem that we think is interesting. So a new algorithm for the learning with errors problem. And when we were thinking about reductions with auxiliary input, this also needs to come up when if we want to get an algorithmic advantage, we better have a good sort of way to convert a good advice for solving P to a good advice for solving S. So the point is that, again, so you can say, well, you know, nobody's ever going to be able to solve the problem P, and then we don't have like and then S is also secure, and we don't have a problem. Sorry. Yeah, and then we don't have a problem at all. But if you want to sort of be able to sort of get an algorithmic advantage saying, well, maybe someone is going to be able to violate the security of the encryption scheme, and I do want to be able to use it to get an algorithm for S, then we should have like an efficient way to convert the auxiliary input for P into a good auxiliary input for solving S. And for classical reduction, this is automatic because, well, if the reduction is uniform, and if the reduction is uniform in classical, as we said before, then it actually is going to have this property automatically. And in particular, you're going to be able to use the same auxiliary input that you use to solve P also to solve S, because this is the algorithm for S is just to run this thing. So it just needs this phi sub P in order to execute. So this was sort of taken for granted in the classical setting, but since it's going to be less obvious in the quantum setting, I want to give it a name. What we get here is in the uniform in the classical setting, a uniform black box reduction is what we call constructive, in the sense that if you get a good advice, a good auxiliary input or advice for solving P, this also gives you a good advice for solving S. And it's also going to be durable, again, something that we don't think about at all in the classical setting because it's trivial, in the sense that when after you're done solving S, you can still continue and solve P or solve an additional instance of S after the fact. So somehow your algorithmic advantage is not one time. So first of all, I mean, you should have an algorithmic advantage. So you can take your auxiliary input for P and convert it into a good auxiliary input for S. And this auxiliary input should not, run out. So it should be able to last you for as many executions of S as you'd want. So with respect to classical solvers, you have this trivially. And now the question is, what happens in the quantum setting? So you might come up with a case where you have a solver, a P solver, that has quantum auxiliary input. It has quantum auxiliary input, so I'm given some quantum state, phi sub P, and the P solver, AP, actually needs phi P in order to perform its functionality. So we can try to see what happens. We can try to sort of run the same reduction. So we get X sub S, run, like come up with the first instance, send it. It works. We get the output back, Y sub P. But then in this process, the P solver might have measured or performed some non-invertible operation on this quantum auxiliary input, and it somehow changed. So in the next step, we're not necessarily going to have like an adequate quantum auxiliary input. We're going to have some potentially arbitrary quantum state, which is not necessarily useful for solving P. So whatever we do here, so starting from the next query on, we're going to get garbage. And the claim is there's a problem, even if you just have a reduction that makes a single query, because again, like, let's say that you managed to solve for X sub S and you got some Y sub S, but then you're stuck. You don't have, you're going to get some garbage coming out, and you're not going to be able to solve an additional instance of S if you want to. And we claim that this is not desirable. So in the quantum setting, just by having a uniform reduction, it doesn't make it constructive and it doesn't make it durable. These are properties that are sort of worth having if you sort of take a reduction seriously as something that could lead you to an algorithmic advantage rather than just sort of showing an existential relation between problems. So there is a standard way where this is handled in the literature. And this is to just say, well, I can say that my auxiliary input for solving S is just going to be multiple copies of the auxiliary input for solving P. And well, after this sort of prologue, you hopefully understand that while this actually works, this will allow you to solve an instance of S using this quantum auxiliary input. This is not going to be constructive because, well, George Clooney says, no, you cannot efficiently and generally takes the quantum advice for P and produce like a tensor product, produce multiple copies of this state. So this is not sort of algorithmically efficient, and therefore it's not going to give you a constructive. It's not going to give you a constructive reduction. And also, you should, maybe think about durability. Like, let's say that you could. How many copies do you actually need? You're going to need like an a priori unbounded number of copies if you want to solve S multiple times. So it's better not to do it if you don't have to. what we are setting to try to understand in this work is whether it's possible to generically convert classical reductions, let's say just non-interactive assumptions, so just like the PNS that we saw, to the quantum setting in a constructive and durable way. So when can you do this, and when maybe you cannot do this is the goal of this work. And yeah, so we show that in some cases this is actually possible. And in order to
and before we try to solve the problem, we need to sort of come up with the right sort of, I guess, formal framework to actually work on these sort of things. And we need a model for a sort of stateful solver. So as I hinted before, when we think about we can think about an interaction between the reduction and the P solver. And in the classical setting, we're thinking about this interaction as stateless. Sort of every time I make a query, as I'm resetting the solver to its initial state. But in the quantum setting, we're going to start with some quantum state with this quantum auxiliary input, and it's going to evolve throughout the execution because we don't have resources to sort of duplicate it. And therefore, we need to consider sort of a model where we're working with a solver that is stateful. The state can change throughout the execution of the solver. And this is a cool model. It's you can think about it in the classical world, and it perhaps makes sense to think when this is relevant also classically. Good. So we show like sort of a sequence of reductions that in some cases can bridge between sort of stateful and stateless. So we start with a stateful solver, which again sort of takes a quantum state and possibly performs measurements and so on, sort of find a way to simulate, to use such a solver in order to simulate for the reduction a solver that is stateless. So we start with this sort of these one-shot solvers. So this is sort of like I showed in the previous slide. You got some quantum auxiliary input, you make one call, and then all bets are off. You don't know what happens after you made the call. And we go all the way to a stateless solver, which is like the solver that you would that a reduction actually expects. Good, yeah, so in the stateless case, we can just apply the classical reduction. And we do this in a few steps. So the first step is to sort of go from a one-shot solver to a solver that never loses steam. So it's going to keep being a good P solver, even if you make multiple queries to it. It allows you to make more than one query. And for each query that you make, it promises to be a good P solver, but it's not necessarily the same P solver. So what we want for a stateless solver is that sort of every time you make the call, you reset it to the same initial state. Here, all that we're promised is that sort of every step, at every query of the execution, we're going to get some solver that is a good solver for P, but not necessarily the same one. So it's possible that it's going to solve. So a good solver just means that it solves with 1/poly probability. So at every time, it can solve like a different subset of the inputs, and it may potentially even do it adversarially. And to go from one shot to persistent solver, this is an extension of work by Chiesa, Mas, Spooner, and Zandri from last year. And in some cases, this can be done, in particular for like decision-like assumptions. So the case where the answer for the P solver, like this Y sub P, is, let's say, 1 bit or a logarithmic number of bits, or there's only a polynomially bounded number of possible answers, then you can actually extend from one shot to persistent. The next step is to sort of go to a class of solvers that we call memoryless. So what does memoryless mean? Well, you don't necessarily remember the previous queries that were made, but you know that now I'm asking you, like, this is the first query that I'm asking you, this is the second query, this is the third query. So you know the sequential number of the query that is being made, but you don't remember what were the previous queries that were made. So this is sort of an intermediate model. And from this memoryless, we go to stateless. And both of these are sort of shown by simulation style argument. So what we're showing is not that we can actually sort of come up with a memoryless or stateless solver, but rather that given access to a persistent solver, given Oracle access to a persistent solver, we can simulate to a particular reduction, what would have happened if this reduction actually had access to a memoryless or a stateless solver. So this is sort of technically what we do. Yeah.
I have a question.
Okay.
So when you mean, maybe you're going to say that later, but when you mean simulate, do you mean simulate with like inverse polynomial probability or like all the time?
Right, so the simulation is going to have inverse statistical distance inverse polynomial, but it's tunable. You can make it as small a polynomial as you'd want. Okay. So this means that if you know the advantage that your reduction has, then you can set this polynomial to be small enough that you still have advantage.
Thanks.
And these last two steps only work for non-adaptive reductions. So this is sort of something that was asked before. What is a non-adaptive reduction? Well, it can still make multiple queries to the p-solver, and these queries can still be correlated. They can be arbitrarily correlated, but the thing that we don't allow is for you to first get the response for the first query, and based on that, sort of try to decide what the second query is going to be. So we're allowing sort of arbitrarily correlated non-adaptive queries, but we don't know how to handle adaptive reductions. And sort of the main technical part of the proof here is this part of going from persistent to memoryless, and sort of the thing that allows us to do this, right? So you have a solver, and every time it can decide on some adversarial strategy. So it only needs to be able to solve the problem P somewhere, but it can solve it in the place that is least convenient for you. So if it knows the history, if it knows what you're trying to do, then it can fail you. The leverage that we have here is that this auxiliary input, while it does change arbitrarily, it still has a fixed length, right? So just by the syntax of the P solver, it takes an auxiliary input of a certain length. So this evolution of the auxiliary input still has to sort of remain length bounded, and this means that we can use sort of information theoretic techniques to sort of make sure that the solver actually sort of forgets the history, forgets which queries were made, and this allows us to go from this persistent solvers to memoryless solvers. And if I have time, I will try to say something technical about this. The other thing that we show is that this is actually impossible in some cases. So we show that in some cases you can actually do this, but we show that for some search problems. So I said before that this first step only works for like cases where the problem P has, for every input it has only a polynomial space of possible solutions. When this is not the case, we actually have counterexamples for sort of the whole thing. So we can show a problem, we can show a case where you have a classical reduction that sort of works. If you have a classical, it works against any classical solver, but it's not going to work against a particular quantum solver. So under cryptographic assumptions, you can actually not do this, and this also sort of shows tightness of this CMSZ technique, where sort of there it seemed, I don't know, maybe Nick can say more. It seems like there's a technical obstacle in going to sort of larger classes of solutions, but this also shows that this is, at least in that sense, tight. So in that sort of axis, you cannot improve the algorithm generally to work for arbitrary solution spaces. So I have just a few minutes. Let me say a little bit about the technique. I will skip this and talk about this memorylessness. So as I said, so what we're starting from is a persistent solver. So there's an evolution of the quantum state. We don't know what this evolution does except that it preserves the length. And we know that every query that we make, we are going to get an answer, and this answer is going to be sort of a good, it's going to be a good solver for P, but it's potentially sort of depends on the entire history, which is not good for us. So we want to eliminate the dependence on the history. Okay, I explained why this is not enough. I actually wanted the next slide, good. And what we want to show is that we can have, so this is sort of what this simulator does. So it takes this persistent solver with a bound L on the length of the state, and it takes a sampler from the distribution of input tuples. So it needs to know what the reduction actually wants to do, what is the distribution of queries that the reduction makes, and then it takes the actual input tuple, like the actual queries that the actual reduction is making. So it needs to know how to sample from this distribution, and it takes the sample for which we want to simulate. And what it generates is a set of responses Y for these queries X. as would have been produced by a memoryless solver. So this is the notion of simulation that we get. And the way that we do this is, well, I guess it's not very surprising what we're going to do. So we're just going to generate a bunch of dummies. We're just going to sort of drown this solver with so many queries that it's not going to remember which one is the one that we wanted to ask, that we wanted to ask for, and which ones are just sort of things that are that we don't care about. So for every query from the set of queries that we want to make, we're going to generate like a large polynomial number t of dummies from the same marginal distribution. And we just, let's assume that all of the coordinates have the same marginal distribution. So we're going to generate a bunch of dummies, and we're going to plug our actual query that we want to make in a random location in the sequence, and then we're going to just make all these queries in sequence. So dummy, 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 somewhere the actual x1 that we want to make, a bunch of dummies, and now we're going to start a sequence for x2. So some dummy, dummy, dummy for x2, and then the actual x2, and so forth, and all the way down the line. And we're going to get sort of a bunch of answers from this persistent solver. And, well, not surprisingly, we're going to take the answers that correspond to the actual queries that we want to make. And this is what we're going to output. And what we prove, I'm slowly converging towards the end of the talk. What we prove is that sort of at the end of each of these sequences, the prover does not remember that we made a query x1. So essentially, the state of the solver, I think I was saying prover all along, where actually I meant solver, but the state of the solver at this point the state of the solver at this point is actually statistically close to the state that it would have had if instead of the true query here, we would have had another dummy. So whether there was a real query here or a dummy query here, you would get essentially almost the same state at the end of this sort of first phase. And this is going to be enough because now sort of inductively we can say the same thing for the second query and so on. So the solver has the answer in a memoryless manner because the state that it has here doesn't remember or is indifferent whether you actually made a query here or did not make the query. So you might as well not have made a query, and then you have a memoryless solver. And the way this is proven is sort of using, so we just need to consider a single sequence. And we're using sort of, I'm just going to say what the argument is. We're going to think about sort of two cases. One where we're running a bunch of dummies, then run our actual query, and then continue running dummies. And we're going to consider the joint distribution of all of these quantum states and the output one, so all the way down here, including the x star and y star, and the final step. And we're also going to consider like the case where instead of running x star here, you're actually continuing to run with the dummies. So you need to be a little bit careful here because, well, as I said, we can't. This is not like an algorithmically feasible experiment because we don't have multiple copies of this state. But it's actually, so you have to be a little bit careful and argue that sort of a posteriori, if you have like, let's say, classical description, like the density matrix of this state, and also condition on all of these sort of classical values, then actually this state is also completely determined. And then you could actually then it is actually well defined to consider both this branch of the execution and this branch of the execution. So you need to be a little bit delicate, but you consider the joint distribution of like all of these the shaded blue experiments in both of these cases, and you show that if this number of dummies is large enough, then these two distributions are delta closed, and you use this and you do this using information theory. Essentially, you show that sort of the mutual information between this and this is bounded, and then you use Pinsker. So this is all I'm going to say about how the proof works. I'm going to say very briefly something about the counterexample because it's fairly straightforward. So let's consider the following classical reduction. So we can consider a signature scheme, and we are thinking about the reduction between violating the security of the signature scheme for one message and violating the security for two messages, two random messages. So we have an adversary that if I give it a random message, then it gives me a valid signature for this message. Now I want to get an adversary that I give it two random messages and gives me valid signatures for both of these messages. So in the classical world, this is very easy. I'm just going to sort of query my solver twice, and with some good probability, I'm actually going to get good responses for both of my messages. If it's a good solver for the single message problem, it's also going to be a good solver for the two message problem. However, in the quantum world, there's this very nice construct that's known as tokenized signature schemes. And this allows to generate like a signature scheme together with a signing token. And the signing token allows you to sign just one message and not more than that. And this is sort of exactly what we want to say. So just take the signature token to be your quantum auxiliary input, and you exactly, just by sort of definition here, you get a solver that can sign a single random message, but cannot sign more than one. So we just sort of rely on the proof of security for the tokenized signatures and just essentially notice that this gives you, yeah.
Is it a conditional result? What's the assumption behind?
Right, so tokenized signatures are known to exist under, I think, in the existence of classical post-quantum indistinguishability obfuscation. There's also the first one by Ben David and Satat, I think is relative to a classical oracle, but you can use obfuscation to replace this. Yeah, so it's conditional. It's based on a cryptographic assumption. I guess, yeah, how plausible it is, good question. But it's maybe, okay, so here's another motivation to construct tokenized signatures from more standard assumptions. I will wrap up because I'm like really used more than the time that I wanted. Yeah, so we need to reestablish cryptography in the presence of post-quantum adversaries in general, in the presence of quantum computers. And so the point here is that we need to also think about sort of the modeling, what we want from a reduction, what we want from a cryptographic result. Yeah, I guess I should also mention, like in this sort of grand framework of trying to take big chunks of classical crypto and convert it to quantum setting. There's a lot of work done on converting results in the quantum random oracle model to the quantum set in the random oracle model to the quantum setting. In particular, you can show also some classes, again, in that context, also some classes of reductions that convert and some that don't. Yeah, in this work, we're considering sort of the role of auxiliary input. And we think constructiveness and durability are something that are worth thinking about. Even just algorithmically, like, could you think about a quantum auxiliary input that would allow you to solve learning with errors once, but not twice? This is, I mean, it sounds counterintuitive, but do we really know that this cannot happen? So I mean, I think even sort of in the strict algorithmic sense, it's maybe worth thinking what kinds of problems. So we were thinking about cryptographic problems, and actually, I think this only makes sense in the average case setting. But sort of just think about computational problems in general, even outside the cryptographic setting, and think whether it's possible to have sort of I guess a tokenized solver for some kinds of problems, because it would be really annoying if like you could do this. If I could give you some quantum advice, or maybe useful also. I don't know if it's annoying or useful. I guess both. If I can give you some quantum advice that will only allow you to solve the problem once or 3 times or something like this. Yeah, so you know what I did, so thank you.
Thanks, Zvika. Questions?
Hey, great talk. So you have this sort of third. So these like different kinds of reduction, right?
Right. Yeah. I'll try to go back to the slide.
I'm trying to remember what they're called, but
yeah. So it's the persistent and memoryless and stateless.
Stateless, right? So yeah.
Stateless is the last one. Stateless is what you want.
Mm-hmm. So once you get to stateless, like, does that mean that you can apply this to interactive problems as well, right? So the question I was asking earlier was like, you can think about an interactive algorithm as being like a non-interactive algorithm where it has like, you know, the input is divided into the different parts, right?
You send the transcript every time.
Exactly, right? Yeah. So I mean, once you have something stateless, does this mean that you can sort of apply this to interactive?
Right. So I think also I think we sort of just gave ourselves a little bit of an easier time, saying, well, you know, the interactive setting is like there's some problems there, so we should just focus on non-interactive. But I think a lot of this framework should also apply for the interactive setting. And again, you can also think about a stateless algorithm, which just takes a transcript and outputs a response. And if you have a stateless solver for an interactive problem with this property, then you should be able to run a classical reduction. I think so.
Okay, thanks.
Guess I told you everything you needed to know.
Right. So I have one quick question. There is actually a work from Fang Song that states general conditions under which classical reductions can be translated to post-quantum.
Right.
Are you aware of this work?
I think I know what paper you're talking about. I'm trying to remember, but I don't remember the details right now.
So
You want to see how
how
it relates?
No, I'm wondering how it compares to sort of the.
I don't remember, but I do think that the issues of sort of being constructive and durable are sort of were not explicitly considered before. So if you're allowing sort of this duplicate, just showing an existential statement, there exists quantum auxiliary input that will allow you to solve S, then you still run into problems, but it's a different sort of set of problems. And I think this is what this paper is doing, but I don't want to commit.
I see. Thanks. Good. So if there are no more questions, let's thank Zvika again. Okay, so we're going to have 3 talks for today's workshop, and to avoid splitting Nick's talk in the middle, maybe we're going to take like 10 minutes now and 10 minutes after the Nick's talk. So we're going to split the break in 2, and so we can reconvene at 10:10. Meantime, we can set things up with Nick.